Hello dear friends, welcome to my channel. Today's discussions is group theory. Which of the following are incorrect? Every group of order 505 is cyclic. Every group of order 51 is cyclic. Every group of order 151 is cyclic. Every group of order 30 in which 2 SSG unique is cyclic. So friends, let's start our solution. Let order of G equals to P dot Q, where P less than Q and P comma Q are co-prime. P comma Q are co-prime if P does not divisible by Q minus 1, then capital G is cyclic. And if P divisible by Q minus 1, then there exists capital G which is cyclic, and there exists G which is non-abelian. Abelian. Okay, which is non-abelian. So option A, you will see what is my option A. Option A is 505. So 505 is cyclic or not? So order of G is equal to 5 into 101. Now 5 divisible by 101 minus 1, that implies 5 is divisible by 100. So G not to be always a cyclic group. Option B, every group of order 51 is cyclic. So we will check this problem, that order of G equals to 51 is equal to 3 into 70. So 3 does not divisible by 16. So G, that implies G is cyclic. Option C, order of G equals to, what is option C? Please check. So option B is correct. Yeah, I see option B is correct. and option A, this is the incorrect. So this is my absolutely, this is false. Okay, so option C, 151 is order of G is equal to 151. This is prime number, so it is cyclic. Now option D. Option D, order of G is equal to 30 into 5. So order of 2 SSG is cyclic. Order of 2 SSG is 2, so it is cyclic. So correct option. So this is also true. So my first option is incorrect. A is incorrect. This is asked in my question. Next, the number of maximal ideals in Z27 is option A is equal to 0, option B is equal to 1, 2, 3. Okay, so there is a theory that number of maximal ideals equals to number of distinct prime divisors. Distinct prime divisors. So divisors of 27, that is 1. So theory is number of maximal ideals, number of node. You need to remember number of maximal ideals of z to the power z e to the power n equals to number of distinct prime divisors of e to the power n. So next question is, which of the following is our Euclidean domain? Z root over minus 3, z root over minus 3 root over minus 3 never UFD. There is a theorem, remark, z root over minus n is never UFD for for n greater than equals to 3. And therefore z root over minus root over 3 never UFD, so it is not ED, because every Euclidean domain is UFD, but converse is not true, means every unique factorization domain is not Euclidean domain. Okay, so if it is Euclidean, it is not unique factorization domain, so it is not Euclidean domain. Now next is ZX. Okay, so this is the option, it is not possible. Next is ZX, this is not possible. ZX is never PID, because Z is not field, so ZX is not ED. Next is RX is a ring, and X is an ideal of RX. Okay, please check R x square comma x cube if equal to AI linear combinations. So we know that Rx is a ring, Rx is a ring, and X is an ideal of Rx. So friends, given that a ring R x square comma x cube, it has an ideal x square comma x cube. Okay, it has two ideal, which is not principal ideal because it is generated by two elements, which is not principal ideal because it is generated by two elements. So friends, two elements means x square and x cube, so it is not principal ideal domain, so it is not R x square comma x cube is not PID, principal ideal domain is not PID, so it is not, that implies it is not EID, not ED. So friends, my next question is this, number D. D is ZX divided by 2 comma y or 2 comma x, 2 comma x and y, that is equivalent to Z2y, and as a Z2y, so it is ED. So my option